So can you guys see my screen?
Yes, we can.
Okay. So yeah, this is like a quick introduction to neural networks for beginners, and basically what this is meant to do. Because I'm assuming that most of us are members of the data. I'm assuming that most of us are members of data community in the lab, right? And there, our primary focus is data science, data analytics, data engineering, machine learning, and AI. But recently, we haven't been getting much traction when it comes to ML and AI. So this session is more like a like just trying to introduce that to people so they can get familiar with it. And I know you possibly already have some experience in data driving. But so if you already have some experience, this will be more like a refresher for you. Yeah. So for this session, you will need to install some Python libraries. You need to install PyTorch because it's going to be hands-on, right? So you need to install PyTorch, NumPy, Matplotlib, Torch Edition, and then so I've created a repository for you guys. Let me share the link now. Um, Ayodeji, Ayodeji, raise your hand.
Yeah, David, can you hear?
Yeah, I can hear you.
Yeah, please, can something be done about your background? There's voices in the background, and it's interfering. Yeah, please. Thank you.
Okay. Okay, can you guys hear me now? Okay, so like I said, I wanted to share a link to the GitHub repository. So if you check the chat, there is a pinned message. Can you see it? All right. So that is a link. So that's a link to the like the finished product, the finished script and everything we are going to be writing, right? So what you are going to do is um if you have GitHub desktop, that would be nice. But if not, you can go here, download it as a zip file. Are you guys with me? So it's really help if you guys are with your PC right now. So go to the link I sent under code, download as zip. Then you can extract that to your laptop, and then whenever you're done, just type ready in the chat. Please leave a thumbs up or type. Okay. I said I dropped a link in the chat, right? So click on that. It's going to take you to the GitHub repository. If you know how to use already, that would be nice. If not, go under code, then download zip. So when you are done with that, you can extract it on your laptop and then type ready in the chat. Okay, that was one. One person is ready. Two, Fatia and Abdulhamid Bello. That's nice. I'm going to wait for, let's say, three more people. So if you are still trying to set things up, just leave a thumbs up. Hi, can you guys still hear me?
Yeah, we can.
All right, I said if you are still like trying to set things, what? What was that? Abdulhamid, you were saying something. I didn't get that. Oh,
I don't think that was me.
oh, okay. Well, like I was saying, I'm waiting for, let's say we have at least five people who are ready. So right now we have two, Fatia and Abdulhamid. And please, if you're having any issue with this, just raise your hand so I can address it. Thank you. Still waiting for three more people. Mm. Okay, that's three. I've seen Israel. Two more. Either way, by 4:40, we should be starting regardless. All right. Let's move. For those that have set it up already, install. You need to install some packages, right, and some Python libraries. I've already included them in requirements. So what you're going to do is go open your terminal, and then install everything that's in this requirement. So you can just do pip install -r requirements.txt. So this is just to make things easier instead of having to install like each of them individually. So all right, while we are doing that, you can go through the notebooks that I have ready here. Um, so this workshop is going to be divided into five parts. Can you still see my screen? Okay, into five parts. So firstly, we are going to do the introduction and the setup. We're already setting up right now. So while those libraries are installing, we can be talking about the basics of this, right? Then after that, we want to implement a neural network from scratch. Then, so we are going to do one from scratch rather than doing one, rather than creating a network with PyTorch or any other library. So doing this is going to give us a feel of how neural networks work under the hood, right? Then after that, we want to load MNISTs. I'll talk a bit more about that later on. So at the end of the third part, we would have created our own neural network and then we'd have a look at MNIST, right? Then in section 4, we will look at PyTorch. I'm using PyTorch to create more powerful neural networks. Then at the end, we'll compare our network with that of PyTorch. So if you are done with the setup, just leave a thumbs up. Okay, Israel is done. Okay, okay. All right. So firstly, what is a neural network? Traditionally, we had machine learning algorithms try to that try to either classify data that try to perform different tasks that human that so neural networks were created to mimic the human brain, and they are useful in identifying the underlying relationships in data. So mainly they work by recognizing patterns, and they can be used for classification, for regression. So just as a refresher, in case you've not come across these terms before, classification is when we have, um, for example, if you have a bunch of images and then we have to determine whether it is a cat, a dog, or a car. something like that. That is a classification task. Regression is when we have mainly deals with numbers, right? So we have, um, let's say you know some things about an area, and you want to determine the average price of houses in that area. So something like that is a regression task. And then, so like I was saying, traditionally we had machine learning algorithms that could work with things like this. But as tasks become more and more complicated, we needed something more powerful, right? So then came neural networks. Now, how does a neural network operate? So the basics of this um, is twofold. Initially, we have the forward propagation and then the backward propagation. So um, if you can see this image that I have here, this is like a very, very basic example of a neural network architecture. This one is called a multi-layer perceptron because it has multiple layers. So at first, we have the input layer where we are taking in input from our data. In this case, for the classification example, the data might be a set of images. For the regression example, the input might be maybe like different factors that we can feed into the neural network. Then the input goes into the hidden layers, which does a lot of things under the hood. Then eventually it is passed to the output layer where we get our final output. For classification, the output um, is usually depending on the number of classes you want. So in the original example where we were trying to classify images as either cat, dog, or car, we would have three output nodes rather. So output one will tell us how likely it is to be a cat. Output two is how likely it is to be a dog, and then output three is how likely it is to be a car. For regression, um, it actually varies, but we might see for that particular example that I gave, predicting the average price, we might just get one output because we need just one number to predict. We need just one number to describe the price of a house, right? So the key components of any neural network are neurons. So a neuron is the basic unit that processes information. If I go back, if I go back to this image that we have here, each circle or each node that you are seeing is called a neuron, and it takes in data and it takes in data and brings out some values as output. So neurons take in data, process it, and then pass the results through an activation function. I'm going to explain all of that later on. So a bunch of neurons are called a layer. So in this case, we have three layers: the input layer, which has three neurons; the hidden layer, which has four neurons; and then the output layer, which has two neurons. And there's a reason why they arranged it in this way. Mainly, and I'm going to explain all of that later on as well. Then, um, then another key component is the loss function. All right, so the loss function is basically an evaluation function to tell us how good the network is. So originally, when we initialize our neural network, it's going to perform very poorly, and we can say that the loss is very high. So after training our network over a period of time, you see that the loss actually reduces.
um, to and settles to a certain value. So at that point where the loss settles, we can say the neural network is has reached its peak or is like optimized. All right. Then after that, we have the optimizer. The optimizer is an algorithm that adjusts the weights and the bias to minimize the loss function. For this particular workshop, we are only going to be using SGD, and I'm going to explain what that is later on. All right. So while we were going through this introduction, how many people have set up? How many people have like gotten this repo on their PC, and how many have installed the packages as required? If you have, just leave a thumbs up. I'm only seeing one thumbs up. Is there anything wrong? Please, if you're having issues setting up or anything, just raise your hand and I'll address it. Okay. 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 So, like I was saying, okay, Abdul Hamid is still installing his requirements. That's fine. We haven't started. We haven't run anything yet, so don't worry about that. So, like I was saying, a neural network operates. The basics of neural networks is twofold. We have the forward propagation and the backward propagation. Um, the forward propagation is going from input to output. That's where we evaluate the output given a certain input, right? And then the backward propagation is where we actually train the model by propagating the error back through the network. So I'm going to give an example of that. Let's say you guys can see this. You guys can see this image I have here. It has it has three inputs, four hidden neurons, and two outputs. So this could represent anything really. Um, but let's say we are trying to get let's say this is a classification task, and then one output one tells us how likely it is to be good. Output three tells how likely it is to be bad. The three inputs, I can just make something up. Let's say we're trying to classify emails as um, normal or spam. So input one could be telling us how long it is. Input three, so you get things like that. And then the output one is how likely it is to be a spam email. Output two, how likely it is to not be a spam email. All right. Then the forward propagation is basically taking our inputs, passing it to the hidden layer, and then passing it to the output layer where we get our results. Then when training, we compute something called gradients. Then these gradients is passed back to the hidden layer to update this to update the hidden layer. Then the gradient is passed back to the input, or not necessarily, but it's basically passed back until we reach the input layer. Um, and that's we are going to see the inner workings of this when we are implementing our custom neural network. So I'm still waiting on you guys to set all of those things up. Mm. Meanwhile, I want to let's have a look at the a neuron. So in that diagram I showed you, we had a bunch of neurons, and each neuron, let's say I'm taking the input, the hidden neurons as example. Each of them takes in inputs from different sources and then produces one output each. Hold on. So this input can either be from a previous layer or it can be from the data that we provided it. Okay. Then the output is going to be passed through an activation function. Yeah, I'm just going to call it f of x. And then when we have that, it is then um, passed to the next layer. So the way the inputs propagates from layer to layer is using weights and biases. I'm going to explain that in a um, so let's say we have something like this. Let's say we have something like this. We have Yeah, this neuron is taking in two inputs. The first one is 1.00, the second one is 2.00. And then, like I said, each neuron is going to have a set of weights and biases, right? So the weights, hold on. Okay, I'm just making some things up here. Let's say the first weight is 2.0, and then the bias is, I don't know, zero point 0.8. All right, so we can have something like this. Then the activation function, I'm just going to leave that for now. The neuron actually takes in this input, multiplies it with its weights, and then adds on the bias. So if we are going to walk through it as if we were the input ourselves, we would have 1.00, that's input 1 times the first weight times 2.0 plus input 2, that's 2.00 times the second weight, which is 3.5. Then finally, we add in the bias, which is zero point 0.8. And calculating all of this is going to give us a value. That value is then passed through the activation function. Like I said, I'll talk more on that later. Passed through the activation function and then returned to either the next layer or as the final output of the network. So this the way I'm doing it now is going to we are going to like look at this for every single neuron in our network, and that can get very, very, very slow and inefficient. So in this example, in this workshop, we are going to be batching all of these operations up and using matrix multiplication. So you see that when we're actually implementing it. All right. So I'm going back to VS Code. Hopefully, hopefully you've installed it already. So like I was saying, um we have Z in this case is our output, W is our weight, X is our input, and B is our bias. Um, in case you are wondering why we even need a bias in the first place, is there are some cases where let's say our data is we're having very small inputs, maybe 0.001, 0.002. When you multiply that by your weights, it doesn't really matter what your weights are. the output is also going to be very small. So we had a bias to artificially increase that output so that the neural network doesn't die off. Um, but you won't need to worry about that. So like I was saying, we have the weights multiplying the inputs, then adding on the bias. That is going to give us not our final output, but we'll call it Z. So we are then going to apply the activation function. In this case, that's G. Applying the activation function is going to be the final output of that neuron. So that's how forward propagation works. Then when training the network, we do something called backward propagation. That's where we update the weights and the biases. And okay, so initially or traditionally, the way neural networks work, most of the ones you are familiar with are supervised, meaning you already know, or let's say you already have a data set of inputs and their correct outputs, also called labels. So you have inputs and you have labels. If, for example, the input here is 1 and 2, and our output is 5, but the correct output should be something like 8. You see that there's a difference between our predicted outputs and the final outputs and the correct output rather. So that difference is what we call the error. And the error is um, passed backwards through the network. So we are going to, when we're actually coding this, we'll look at how all of this works, right? All right. Then, like I said initially, we have weights, biases, and then this calculated value is then passed through an activation function. So what an activation function is basically something that makes the neural network non-linear. So without it, it's just like, the only operations we've done so far are multiplication and addition. If you multiply and add different inputs together, your final answer can only be a linear function of the inputs, right? So if you without activation functions, it can only learn a linear relationship. And not all data is linear. For example, if we were to, let's say we are trying to do a regression task, and our data input to output relationship is quadratic, meaning maybe we have something like y equals to x squared. Without activation functions, the only thing it can learn is a straight line, and you see that it's going to have a very, very high error. So to battle that, we are going to introduce activation functions. Um, the most common activation functions are sigmoid, relu, tanh, and leaky relu. So sigmoid looks, I really prefer it if you guys had this on your system. Not everybody is done setting up. But don't worry, that's fine. So I'm going to run this. Let's have a look. So the first one that we have is sigmoid. It takes in any input from minus infinity to positive infinity. It doesn't matter what the input is. The final output is going to be somewhere between 0 and 1. That's what sigmoid does. It takes in any input and returns 0 or 1. And as you can see, it's not just a straight line, it's curved, meaning using this in your network can enable it to learn non-linear relationships. Okay. Then next we have ReLU. Um, that's rectified linear. Okay, I've forgotten the full meaning. I think we can we can search that up. So ReLU starts for rectified linear units. It's basically something that if a negative input returns zero, and then positive input returns. And I know you might be wondering, but is this not a straight line? Like I just said, we are trying to introduce non-linearity. But believe it or not, this is usually good enough in most cases. Sometimes ReLU even performs better than sigmoid. So just keep that in mind. Then we have tan H. Looks very, very similar to sigmoid, but in this case, it squashes any input between -1 and 1. And in some cases, it also performs better than sigmoid. So for some people that might be concerned with this behavior of ReLU, where negative values are returning zero, then we introduce leaky ReLU rather. Leaky ReLU works by taking is the same with ReLU, but instead of returning zero, it just returns a small value, not necessarily zero, but a very small value. Um, so now you might be asking, how do we choose an activation function? And to be honest, that's a very very good question. Usually, there's no hard and fast rule about it, so you might have to experiment with a few of them. Um, so that's the basics. We've explained the structure of a neural network. We've explained how a neuron works and how it takes in inputs and brings out outputs. So moving on, we are going to take all this and put them into practice by creating our own custom neural network. So it's at this point that I really, really, really want us to follow along. All right. If you install those libraries, then we are going to run the first cell. This is us importing NumPy and Matplotlib, and then hold on. All right, and then I'm setting a random seed of 42 because I want what I'm getting to be what you're also getting. So for reproducibility. So we've imported NumPy, we've imported Matplotlib. Now what we are going to do is basically everything we talked about in the introduction. We are going to be implementing it in code. It will be advantageous for you if you already know how to use NumPy. But if not, don't worry, that's fine. So we are trying to create a neural network from scratch, has something like this, a three-layer network that has inputs, hidden layers, and outputs. So in the when initializing, we can see that we have the input size, the hidden size, and the output size. Okay, this hidden size is something that we call a hyperparameter, which is like something that defines the network's architecture. So it's something that while training, we can't change the hidden size. We can't change the input and output size either. Um, Another example of a hyperparameter is this activation function that we have here. So while training, we can't change the activation function that we are already using. Okay. So initially, like I said, the network is initialized with a bunch of random weights and biases. Instead of, hold on, let me go back to where I was explaining this. Remember, I said it takes each neuron multiplies I was saying that each neuron multiplies um, the input by its own weight and its own bias, but that's like very, very slow. So instead of doing it neuron by neuron, we are doing it layer by layer. So we can have something like this, and then we can calculate the values for hidden layer at once from the inputs. How? By batching up all of these weights and biases as a as a matrix. So if we have where are we? This neuron has two weights. The next neuron is going to have two weights. And the neuron after that two weights. So instead of doing each of them one by one, we can have a matrix. So we can have something like this, where so instead of calculating them one by one, we just do matrix multiplication and then multiply the combined weights by the inputs, and then add on the combined bias to get the final like combined output. If you have any questions, just raise your hand. So that's what we are doing here. We are initializing the weights and biases with random values. Um, so the first weight that's between the inputs and the hidden layers is going to have n rows and m columns. The number of rows is the input size. The number of columns is the hidden layer size. Um, right? Then the for the bias of the first layer of the hidden layer is going to be a matrix that has this number of columns, the hidden size. And then for this particular network, we are going to be using sigmoid as the activation function. So initially here, when I was explaining what the activation functions do, we have we have formulas for it. So for sigmoid is 1 divided by 1 plus e raised power minus x. And then that's what we are implementing in code here. Okay, so that's the sigmoid. And then to calculate the error, what we do is we take the derivative of the activation function. That's so if you are familiar with calculus, you can differentiate this expression, and you're getting this as the derivative. Um, so That's what we are using for the hidden layer, and then for the output layer, we are using softmax. Um, softmax is an activation function um that let's say it deals mainly with probabilities. So if you are trying to classify if you're trying to do perform a classification task, and then the outputs are having something like 1 2, we want it to be in form of probabilities, maybe 30% to 70%. So that's what softmax does. And then notice that we don't need to take the derivative of softmax, because that's the final output. So in our forward propagation, what we have is What we have is, we are, like I said, we are going to multiply the inputs by the weights and then add the bias. So that's basically what this is. We are multiplying the inputs, that's x, by the weight, which is W1. W1 is for the hidden layer. So and then we are adding the bias, which is B1. That value that we got, we are passing it through the sigmoid activation function. And this is the A1 is the output for the A1 is the result of the hidden layer. So that A1, we are going to pass it through to the output. We are multiplying A1. Dot means dot multiplication. So we are multiplying A1 by W2. W2 represents our output, the weight between hidden and output. So A1 by W2 and then adding B2. So after doing that, we get Z2. Then we apply softmax to it. Like I said, softmax is basically we're trying to turn it to probabilities. So um, we apply softmax to it, and that value or those values are our final output for the forward pass. So for backward propagation, I'm going to come back to that. So we've seen how the forward pass works for this particular one. To make predictions using this using our custom neural network, we basically take in inputs, run the forward pass to get some outputs, and then return the highest one. As simple as that. All right. Um, I like I said initially, we need to have a training data set, meaning we need some inputs with the correct outputs already. For this one, we are going to use XOR. XOR is a binary operation. If you are familiar with logic gates, it's something that takes in either zero or one, two inputs, and then returns one output. So for this case, we're having four sets of inputs and outputs. When we have 0, 0, the correct answer should be 0. When we have 0, 1, the correct answer should be 1. When we have 1, 0, the correct answer should be 1. When we have 1, 1, the correct answer should be 0. So basically, if the two inputs are the same, return 0. If they are different, return 1. Now, the reason why I chose this data is because it's not linear, and it's not something that can be easily classified. So this is like normally if you are getting started with coding, you usually do something like hello world. So XOR is like the hello world of neural networks. So um what we are going to like I said, the inputs, we have two inputs, right? It's either taking in 0, 0, 0, 1, 1, 0, 1, 1. So our input size is 2. Then this hidden size is up to us. I'm choosing 4 for this case. If you want, you can tweak it a bit, and then if you want, you can tweak it and just see which one works best. So, like I said, is this hidden size is a hyperparameter. It's something you can use the network architecture. So the output size is um hold on. But I just remember that I haven't really explained the training loop. So the way our training works is that we run what we call epochs. So one epoch is like one one step of the training. Um, so the first thing, the way our loop, sorry, the way our loop works, like I was saying, is that firstly we run the forward pass. Please, how many people have installed those packages now? Uh-huh. So the first thing we do is to calculate we run the forward pass, which is the output, taking in the inputs and returning the outputs. Then we calculate the loss. Then we calculate the loss, and then we are going to append it to our losses. So the our loss function is, remember what the loss is basically telling us how well, or sorry, how badly the network performed. Um, we are so we need the output and the correct value to be of the same size first. So this neural network, this particular one, produces two outputs. The first one is the probability that the final answer is zero. The second one is the probability that the final answer is one, right? So it produces two outputs. But where is it? Our if you check our data sets, we're only getting one. So we need to first like process this y array to be of shape two, like to be having two columns each instead of one value. So that's basically what we are doing here. Firstly, we create that process is called one hot encoding. Is where we have a value, or like a class, and we are trying to turn it into an array. If you are using, we basically use that for classification tasks. If you are using the cat, dog. So if you're having a look at the cat, dog, car example from earlier, we can, let's say if the final answer is cat, we can say something like 100. If it's dog, 010. If it's car, 001. So the place with the highest value is telling us which class we're actually predicting. So that's what we are doing here. So remember, y is going to have just initially is having just one value. We want to do one not encoding. So we are taking in just a bunch of zeros, and then and then we are setting the correct ones to 1. That's basically what I just explained now. So taking this 1 hot with the correct output, sorry, the output of our neural network is this, and then the correct values is y1 hot. So we are taking those two and we are computing the loss using that formula. Um, using we are just going to be keeping track of that by adding it to a losses list. Eventually, we are going to plot that list, like that list, to just show us how well our model is performing. So, um, where was I? For after that, we are going to run our backward propagation. I know I didn't explain this earlier, so but this is the backbone of neural networks. This is where we actually update the weights and the biases to improve the network's performance. So first thing we do is again one hot encoding, the same thing we did here. So we are turning the class to a list. That's just all it is. Then we calculate the difference. Like I said, we need to first get the error. So we calculate the difference between our value and the correct value. So output minus y1 hot, right? And then if let me go back to the drawing board. Remember, we're having something like y equals x times w plus b, and all of that is passing through the activation function f. So what we want to do is we want to take a gradient, meaning we are differentiating y with respect to either w or b. Um, you don't need to know calculus for this, but if you do, we apply what we call chain rule. So we are differentiating one, the output of where is it? A1 is the so hold on. Our input is going to our hidden layer, which I'm calling layer one. A1 is the final output of the hidden layer. A2 is the output of the output layer. So we are taking so we are taking that A1, transposing it and multiplying it with the error. Um that's for the where is it? Where is it? For the outputs, we are using softmax, but for that one, we can just consider it as like before calculating the probabilities and all that. It's just this, right? If you differentiate this expression with respect to w, that's just x, right? So in this case, remember we are starting from the back. So in this case, the w is w2, and the x is what we are getting from our hidden layer, which is a1. So that's that, and then we just multiply it by the error that we got initially. So that's what we are doing. A the W2 is A1 multiplied by the error. For B2, if you differentiate this, it's just one, right? So it's just one. We are adding up everything. We're adding up all the errors. So multiply this by the error, which is dz2, right? And then adding all of that up. So it's just the same thing with adding this dz2 up. So that's one. We've propagated from the output back to the hidden layer. Then the next step is to go from the hidden layer um, back to the input. So what we'll do is we multiply this error, that's dz2, by um, w2. Okay, and then we are going to take the derivative of our activation function. That's this. Activation function is f. We are taking the derivative of that, which is f prime, or sigmoid derivative, and then we are applying that to a1. So eventually we're going to have a bunch of dw1, db1, dw2, db2. These are our gradients, and these are the things that we're going to pass back, that we're going to propagate backwards from output to input. So basically, this um, if you have, let's say let's say our final output was 5, but we wanted 8. 5 minus 8 is minus 3. I mean, the other way around. Yeah, 5 minus 8 is minus 3. So we are going to, whatever caused this error, we are going to negate it. So in essence, what we want is 5 minus minus 3, which is plus 8. So in theory, when you negate the gradient, it's going to give you the correct value. So that's what we are trying to do here. We're trying to reduce W1 by the gradient of W1. But you see, we are multiplying by this parameter called the learning rate. Um, the learning rate basically tells us how fast or how slow you want the model to update. If the learning rate is too high, it tends to overshoot and might not settle at a particular value. If the learning rate is too low, it will settle, but it will take a very, very long time, right? So um, again, there are some algorithms that can select a learning rate for you, but for this one, we are just going to have a learning rate of 0.1. All right, so this is where we are updating the weights and biases, and then we are just going to log that. So I'm coming here to our mm, so I'm coming here. This is where we are like testing it. We initialize our neural network from scratch. The input size is 2 because we have 2 inputs. The hidden layer size is 4. We just chose that at random. Then the output size is 2 because we have two things that we're classifying. So notice that this one, I'm choosing to make it a classification task. Like we're either choosing 0 or 1. It's on purpose. Initially, you might, maybe because you're seeing numbers, you might think that we would have used maybe regression, that we're trying to get a single value. But know that for this particular example, a value of um a value of 2 does not really make sense, right? We want either 0 or 1. That's why I'm making it classification. So we train the neural network using a learning rate. I just set zero point 0.5. I think when I was running this on my laptop, zero point 0.5 was okay. So zero point 0.5, and then for 5,000 epochs, meaning we are running this training loop 5,000 times. So let me do that. So as you can see, initially we started with Um, it started with 0.693, 0.6932, and then we ended with 0.6931. Doesn't look like that much of a difference, but if you zoom in on that, you see that initially it started with 0.69322 and it ended with 0.69315. The reason why is, of course, this our custom implementation is very, very inefficient. But but as you can see, the loss or the error actually goes down very, very fast. Then at a point it settles. So um, this is just like a way of, so I'm plotting out the final. I'm plotting it out. So where we had, where is it? If the two inputs are 0 and 0, the value should be what was it? Hold on. If the inputs are 0 and 0, the value should be 0 because they are the same. So that's what we had here. But the network predicted it wrong. Again, I already explained that this is because the one we created is not very optimized. And also it has, maybe the network architecture we are working with is not like, it's not it's not the best to use in this case. But that's that. And what we've done so far is we've implemented something like this, which is a single, it has only one hidden layer. Next is to build a multi-layer neural network. Depending on um, so it's basically the same thing with what we had here, but it's basically the same thing what we had in our custom neural network from scratch. But for the forward pass, we are moving from layer one to layer two, sorry, from input to hidden layer one, hidden layer two, and so on and so forth. Um, so in this one, we're having more control over the network's architecture. Um, I don't have to go through the details of this, but it's like exactly the same thing we've done, except we generalized it to handle multiple layers. And also, just for the fun of it, I'm using Relu. So in it, for the single hidden layer, I used Sigmoid. For this one, I'm using Relu. Okay. Okay. So um, every other thing is the same thing, except they've just been like extended to handle multiple layers. So we're going to test this now. We are creating the same data set, but this time we are using two two inputs, two outputs as usual. But we're having two hidden layers, each having 8 and 4 neurons. So we are initializing our multi-layer neural network and then training it with, I'm using a slower learning rate because basically because we have more layers. So assuming kept on using zero point 0.5, it would overshoot, right? So I'm choosing 0.05 and then running this gives us, so as you can see, it's actually improved. Initially, we had a loss of 0.6959. That really doesn't matter because that was random, right? But if you notice at the end, after 1,800 epochs, our loss has gone down significantly to 0.011, meaning it's almost 100% accurate. Um, so, and as you can imagine, the reason why this one performed better is most likely because of the additional layer that we added. So I'm going to visualize it in the same way we did the other one. Notice the difference this time. Let me go back to the first one we did. In the first one we did, it was only able to divide the space into two by using a single line. And if as you can see, there's no way to divide this into there's no way to divide this using a single line. It's literally not possible. But our multi-layer neural network was able to divide it into three parts. This middle band representing 0, 0, and 1, 1, and then the others. And the accuracy is 100%. So basically, that's what we've done is we've taken this concept that we learned. We've taken this concept and then we've um, looked at how forward propagation works and how backward propagation works, and we applied that to our custom neural network. So for the next part, we're actually going to look at something. We are moving on to a real data set called MNIST. I'm going to, so if you are following along with your if you are following along with your PC, go to notebook number 3, MNIST dataset. So MNIST is like the most basic, should I say, computer vision task. So yeah, we have a bunch of handwritten digits 0, 1, 2, 3, 4, 5, 7, 8, 9, and then we are passing it into our computer or into our model to what predict what digit was written. So again, we are going to import the relevant we are going to import the relevant packages. We are importing NumPy, we are importing Matplotlib, and then we are importing PyTorch. Okay, so we are not actually using any, what's it called? We are not using any um, neural network yet. We just want to have a look at what the what MNIST is. So because of time, I'm not going to go through the loading and pre-processing of these data sets. But if you are following along from your um, if you are following along from your system, you can run everything under section 2 and 3. So doing that is going to show us like an example. So I'm picking random values. For the first one, we have 1, this is 2, this is 8, 5, 2, 6, 9, 9, 9. And for human beings, this is like very, very simple to recognize. But the model that we just created, the multi-layer perceptron, might actually struggle a bit, but we'll see. So again, this time I want to look at how many digits we can find in the data set just to check how balanced it is. So hold on, um let this run. Okay. Okay, so we have almost 6,000 of each digit. We're having like 60,000 images. Then Then another thing I'm going to do is visualize the image properties. So on your own, maybe later when you have the time, you can go through how I actually loaded the data sets and how I'm doing all of this analysis. But this is not the main focus for this session, right? So what I'm trying to do now is like for each, we have 10 digits. We have 0 to 9. For each of them, I'm taking the average image. So we can have a look at like a representative of each label. So something like this. The average 0 looks like this. The average 1 is like this. And you can see that it's a little bit blurry. That's because we are taking in um, different positions, different orientations, and we are like taking the mean of that. But all in all, it looks like this. So finally, what we want to do is um, we want to prepare this data in a way our network can understand. So if you remember, let me go back to the second notebook. The input that we the input that we are feeding in is the input that we are feeding in is a list. Where is it? So is a numpy array. So we're having an array of so size, and then the output is also something like that. So we are going to process this data set to so and then we are going to for the previous first what's it called notebook 2, we trained it on all of the data and we tested it on all of the data, but that's not how it actually works in real life. So usually or ideally what we want to do is train it on a portion of our data, and then to evaluate how good it is, we divide all of our samples into train and test. So training is the one that's actually going through the network and we are using it to learn to update all of the model parameters. Then for the test is actually how we evaluate how good the model is. So we are doing this to prevent overfitting. Sometimes if sometimes the model can perform like excellently on training data, but when you introduce new new data to it, it fails. That's because something like let me put it in human terms. Imagine you are preparing for an exam now, and then you are training yourself on past questions, but you don't actually understand the concepts. So maybe you already know that okay, if this question comes out, the answer is A. If this comes out, is B. So when the exam comes, they are bringing out completely different questions. If that happens, you're actually going to fail. So it's something like that can happen to models that overfit. And to avoid that, that's why we do training and testing. Okay. So yeah, we had 6,000 images. We are dividing it into 5,000 for training and 1,000 for testing. So after all of that, I'm just going through some pre-processing. Um, Basically, what I'm doing is initially, remember when we were looking at the distribution, we saw that one is actually more common, followed by seven, and then the least common digit is five. So I want to balance that out. I want to balance that out, and I'm only picking a subset of it. So this time we are only having 50 of each digit. So 50 zeros, 50 ones, and so on. So after that, I'm saving it so we can use it in the next notebook. All right, and then all of this, you don't actually have to go through all of this right now. But this was when I was just trying to look at how what in which of the samples might be more difficult for the model to understand. So don't worry about that. Okay. So what we've done, we've looked at how um, we've looked at how a multi-layer neural network works. But like I said, it won't really perform well on something as complicated as this. Um, this one has 784 784 pixels. Um, and our model is not really optimized that size. So we are going to use one from PyTorch. PyTorch is or the PyTorch has a neural network has a bunch of neural network functionalities, and we are going to be importing one of their models. So again, I'm seeding it. We are importing NumPy, Matplotlib, PyTorch, and PyTorch's optimizer. Okay, and I'm seeding it with 42, so that if you run it on your end, you're going to get the same. You're going to get the same output rather. So in this case, normally we would use a GPU for things like this, but since we don't have that, it's actually going to be running on our CPU. If you are working with like bigger data sets, we will need to actually get a GPU for that. Okay, so we've set our device to CPU, and then if you remember, we saved in the last notebook. We saved some of the process data, mnist mini, mnist subset. So we're going to import that. We're going to load that into this notebook now. So we have the training data, training input, training output, test input, and test output. But since we are working with PyTorch, we need to convert that to PyTorch tensors. So you don't really have to worry much about what that is. The functionality is almost similar to NumPy arrays. Um, so we are converting the training input to a training input tensor and so on and so forth. Then we are creating a data set, a tensor data set. There are different in PyTorch. There are different ways of loading in data sets, and this is one of them. This is if you already have like the if you already have the values for it. So you can create a tensor data set, passing in the inputs and the outputs. So we are creating our train data sets, taking in the input train tensor, the output train tensor, and so on. Okay, so we've loaded in our data, and we can see we have 5,000 training sets and 1,000 samples for the test set. Okay, so if you remember the multi-layer um, multi-layer network that we created earlier, we can this is where we're actually implementing that in we're actually creating that in PyTorch. PyTorch has a class called module. So as you can see, this is the base class for all neural network modules. So if you are implementing your own neural network model in PyTorch, a it needs to inherit from this nn.module. So Okay, then this is how our architecture looks like. Remember that we had um, we had the input. This here is representing the first hidden layer. So it's taking in 794, that's 28 times 28. The image size is 28 by 28, 784. And then it is outputting 128, 128 values. Then we are compressing that again from 128 to 64, compressing 64 to 10. So the reason why we are using 10 is, of course, because we have 10 classes, 0 to 9. So that's the overview of the network architecture. And then again, we define our forward pass. Firstly, the first thing we do is to flatten the image. So instead of having 28 by 28, we are just having 784 values at once. And then we'll run it through our model, which is stored in this linear ReLU stack. This is where we're defining it, right? And then we pass our inputs through that to get the output. In PyTorch, we usually call the output logits. Okay, so um, then we initialize a model. This is how our model looks like. It is, I've already explained that before. So 784 to 128, 128 to 64, 64 to 10. So you can think of it as having um, two hidden layers, 128 and 64. Now we are defining the loss function and the optimizer. Um, I've already explained what the loss function does. It's basically comparing the output with the correct answer to determine how poorly the network performed. Then the optimizer is, we don't really have to worry about that right now, but it handles some of the hyperparameters like the learning rate. Okay, then we don't really have much time. So if you are following along from your end, we are going to train the model. We already have what's it called? We already have our data loader, our model, our optimizer, and all of that. We are going to train it on that, and we are taking it batch by batch. So training it, the flow is almost the same thing as what I've already explained earlier. All right. Then the test for testing is the same thing, except we are not training. That's what this touch does no grad is for. No grad means don't calculate the gradients. Okay. So we've created that. Now let's run this over 5 epochs, and we can look at how well the model performed. So um the first time it ran, it was already 84.70% accurate with an average loss of 0.5. Then the second time we had this, and then eventually it was 91.40% accurate. So, like I was saying, the PyTorch has lots of optimizations over our naive multi-layer network. Um, so let's visualize the loss For the training, you can see how it goes down steadily. Testing, notice that the test loss is actually higher than the train loss. That's to be expected, of course, but the difference is not as much. Okay, so let's visualize some of the model's predictions. We are testing here. We have an image of the number 7 and it's predicted 7. We have 2 and it's predicted 2. Um, and all of that were correct except for this. To be honest, I'm also confused. Is this a 5 or a 6? So actually, it's a 5, but the network predicted 6. I can't actually blame it for that. Okay, so um, I was going to go into convolutional neural networks, but we might not have time for that actually. So don't worry. Okay, so I've saved the model under models. That's what we have here, and then we are done with this. Originally, I intended on like comparing it side by side, like looking at our custom implementation versus PyTorch, but um, we won't really have we won't really have time for that. So I'm just going to round up now. So one thing that you can notice is that PyTorch was way faster. Our custom neural network, we used 1,800 epochs. But for PyTorch, we just used 5 and it was already 90% accurate. So, okay. And as you can imagine, it was more complicated to code it from scratch. But that was just for the experience. So later on, you can actually go through it and um, try to try to understand the flow of everything. If you are not sure about something, I think you can reach out to me or any of my others on the group. So, um, yeah, all in all, we've built a neural network from scratch. We looked at a real world data set called MNIST, and we looked at how we can create our own neural network using PyTorch. We weren't able to compare them, but yeah, hopefully this workshop has like given you basic a basic fundamental of neural networks and how they work, and hopefully it was a good introduction to modern deep learning networks. So this is where I'm going to end for now. Later on your own, you need to learn about more complicated architectures. You need to experiment with different data sets. You need to dive deeper into PyTorch. And you need to learn how to implement more complicated optimization techniques. So once again, you can check the comments for the GitHub repo. I'm going to push you can all of these notebooks and you can run them from your end. Um, thank you very much for your time. Oh, the call will end soon.
Yeah, thank you so much. Okay, because this is the end of the call.
So yeah, we might have to leave this call. Let's discuss on the main group. Bye.